Hello and welcome to a new video. My name is Herwig and today we discuss the 11 functional groups of polymers. So what are functional groups? They are the recurring atom clusters in organic molecules whose chemistry largely determines material properties such as polarity, hydrogen bonding, thermostability, chemical resistance, chain rigidity, and also degradability. And in polymers, the functional groups present um, present in the backbone control bulk properties and also processing behavior. So identifying the dominant functional group is also a quick route to predicting performance. Okay, let us get started with the first functional group. Okay, Amide group. The amide is a functional group having a nitrogen atom bonded to two carbonyl groups, an alkyl or aryl group, and additionally, alkyl or aryl groups are bond to the carbonyls. You can see this on the left side of me. What it gives, outstanding high temperature stability, good chemical resistance, and a high class transition temperature combined with low creep. What are some examples? So it's many polyamides, such as Kapton or Vesper. The sulfone group. So the sulfone functional group is characterized by a sulfur atom double bonded to two oxygen atoms and flanked by two carbon atoms as part of alkyl or aryl groups. And the central hexavalent sulfur atom is double bonded to each of the two oxygen atoms and has a single bond to each of the two carbon atoms, usually in two separate hydrocarbon substituents. What it gives, high thermal stability, hydrolytic stability, rigidity. We have good flame resistance, good dimensional stability, and toughness in amorphous way. So it's amorphous polymers. And what are some examples? So the polysulfone group, polysulfone, polyether sulfone, and polyphenylene sulfone. The amide functional group consists of a carbonyl group bounded to a nitrogen. In polymeric amides, one hydrogen atom is bonded to the nitrogen together with one alkyl or aryl group. And what that provides us, it's a really strong intermolecular hydrogen bonding, which then as a consequence allows for high strength and toughness and a relatively high melting point. On the other hand, we have moisture uptake, so the hydrophilicity increases with amide density, and we have also good abrasion resistance. Examples are the polyamides, the nylons, polyamide 6, polyamide 6,6, long chain polyamides, but also semi-aromatic and fully aromatic polyamides, such as Kevlar. Esters are a functional group characterized by a carbon bound to three other atoms, a single bond to a carbon, a double bond to an oxygen, and a single bond to an oxygen. And the single bound oxygen is again bound to another carbon. And therefore, esters have the general form R1O2R2, where R1 and R2 can be a variety of carbon-containing alkyl or aryl substituents. And what does this bring now? So the backbone polarity, it provides good mechanical strength. Then we have downside is hydrolysis. So we have a good melt processability. And as example, for esters are polyesters like PET, polyethylene terephthalate. A ketone is a functional group with the structure R1C double bond O R2, as you can see next to me, where the R1 and R2 can be a variety of carbon-containing alkyl or aryl substituents. So ketones contain a carbonyl group, a carbon oxygen double bond, and the carbon is bonded to the two other carbons with a single bond. What does that provide us? We have increased backbone polarity and stiffness when combined with either linkages in high-performance families. It confirms elevated glass transition temperature and also chemical resistance. And typical polymers examples is the polyaryl ether ketone family, which include polyether ketone, polyether ketone, and polyketone ketone, used for high temper structural parts and, for example, bearings. Sulfide functional group consists out of a sulfur atom and flanked by alkyl or aryl groups, leading to the general formula R1SR2. And for example, this provides you then certain high temperature, high chemical resistance. And as an example, we can take polyphenylene sulfide, where the R1 and R2 are replaced by an aromatic ring structure, which then provides this high temperature and also high chemical resistance performance. Ethers are a class of organic compounds that contain an oxygen atom joined by two alkyl or aryl groups. And this is expressed in the formula R1OR2. And what that provides us is flexibility in case of aliphatic ethers, good low temperature toughness, and for the aromatic ether linkages, polyaryl ethers, we have increased thermostability and also oxidative resistance. And example for aromatic ether is polyphenylene oxide, the PPO. So an arene is an aromatic hydrocarbon containing solely carbon and hydrogen atoms, and the configuration of 6 carbon atoms in aromatic compounds is called a benzene ring. We already mentioned that before. And as a functional group, arenes contain benzene, substituted benzenes, and polybenzenes. What that provides us is backbone rigidity, so high modulus, high thermostability, and we have also the aromatic content generally increases the glass transition temperature and heat resistance. An alcohol is an organic compound with a hydroxyl OH functional group on an aliphatic carbon atom. Because the OH is the functional group of all alcohols, alcohols are represented by the general formula ROH, where R is an alkyl or aryl group. What that provides us now is we have hydrogen bonding, polarity, water solubility, and also reactivity for cross-linking, for example, isocyanates to form polyurethanes, or functional modification. And examples are, for example, polyvinyl alcohol. Let's come to alkanes. Alkanes are organic unsaturated aliphatic hydrocarbons with one or more carbon double bond. Alkanes consist entirely of carbon and hydrogen atoms and lack any other functional group. So the functional group is an alkane, which is a carbon-carbon double bond. And what that provides us, low polarity, so low surface energy, excellent chemical resistance to polar solvents, high flexibility, especially with a low glass transition temperature of aliphatic polyolefins, good electrical insulating properties, and very high production volumes, because we are mainly talking about polyolefins, polyethylene, polypropylene, commodity plastics. Last but not least, haloalkanes, also known as alkyl halides, are a group of chemical compounds comprised of an alkane with one or more hydrogens replaced by a halogen atom. Can be fluorine, chlorine, bromine, iodine. And because the halogen is the functional group, halogens are represented by the general formula Rx, where R is an alkyl or aryl group, and X is the fluorine, chlorine, bromine, iodine. What that provides us is increased flame retardancy. So, for example, chlorinated polymers. We have also good dielectric properties. We have also higher density. Examples is polytetrafluethylene, PTFE, or PVC, polyvinyl chloride. Okay, that was it for today. 11 functional groups of polymers. Thanks for watching and see you in the next one. Bye.